Yeah, thanks a lot for this opportunity. Yeah, I'm very sorry for not being there. Unfortunately, I couldn't reschedule my flight, and this was canceled. Yeah, thanks so much for organizers for this wonderful event. Yeah, I'll be speaking today about the graphic representations of several models, which include the POTS model and the Six-vertex model and the Lipschitz functions. And Let's start with the POTS model. So I assume that most of you were also at mini courses last week, but nonetheless, I will just introduce these objects just to be sure that we're on the same page. Sorry. So first of all, we'll start with the POTS model. So this is the model on their we work for the whole talk. We work on the two-dimensional lattices. So now we're on Z2, and the POTS model is supported on colorings of vertices in Q colors. Q is at least two, and their distribution is given by exponential of -1 over temperature times number of disagreements between neighbors. So example for configurations on the right side, this is for free colors, and we count all disagreements. So here between red and blue, blue, red, etc. So now I will, so indeed at Q equals 2, this is just the e-ink model. Let me show you some simulations. So for low temperature, you get ordering. So but if you have red boundary conditions, then everything gets red with small clusters of other colors. For high temperature, you get this picture of very small clusters of different colors. And finally, at critical temperature, you do expect to see this relatively big clusters of different colors. We will be looking at different points of this diagram. So it's known that the transition is sharp, that let's say if you look at the probability of two vertices far away being of the same color, so first of all, they can be of the same color just by pure randomness because each of them has one of the colors of probability 1 over q. So if you subtract this 1 over q, it's known to be this non-negative. At the same time, it's when you are above the critical temperature, these correlations decay exponentially fast, and when below the critical temperature, actually this is you have ordering. So that's there what you see on the left picture of ordering. So now we look specifically at the critical temperature. So here the behavior depends on Q, and if you look at Q equals 3, Q equals 4, so these are the pictures from before. So here you have this big clusters of different colors. Again, it's at TC, right? What's known about this is the following. So that the order of decay of correlations is polynomial, means that actually there's RSW estimate. So it's not known that there's one particular alpha. It's between two bounds for Q2, 3, and 4. And at 2, this is the e-ink model, and their convergence was proven. So here, this polynomial decay rate alpha should be a universal critical exponent, and for e-ink models, indeed shown to be equal to 1 over 4. This is the work of Dima, Clement, and Costa, and regarding their polynomial decay for Q3 and 4. This is the work of Hugo Vladas and Vincent. Now, if you go to Q equals 5 and above, in fact, then their behavior is quite different. That in fact, you either have exponential decay of correlations or you have order, meaning that in fact, you have coexistence of several phases. So what you see on this picture on the right now, there's no uniqueness, that if you put the blue boundary conditions, and actually you will have this ordered blue phase. And if you have free conditions, then you have chaotic free phase with exponential decay. And here I just put all them together, and you have this coexistence and interface between the two. Indeed, in the work of Ramanujan, it was proven that there are at least Q plus 1 states, in this case, Q monochromatic of different colors, and one free. And together with Ion, we proved that these are the only extremal states, and every other Gibbs measure is their linear combination. So now we look at the interface between the states. And again, so here the behavior is different between in two cases. When Q is 2, 3, or 4, you expect to see their Sherman involution, which was proven at Q equals 2. And it's known that the values 3 and 4, you have tightness, so subsequential limits, and these limits have Hausser dimension strictly between 1 and 2. At the same time, when Q is above 4, the conjecture is very different. In fact, you should see somewhat, for the interface, you should see somewhat the behavior which is reminiscent of the subcritical. That the interface behaves like a Brownian bridge. And in fact, this was conjectured in the works of Brickman, Leibowitz, Messager, Miracle, Soleil, Ruiz, and Schlossman. So if you put the conditions, depending on what you put, you'll have a different limit. If you put the conditions blue and free as on the previous slide, maybe I'll quickly go back. Sorry about this. Like here, the interface should behave like a Brownian bridge. And if you put the conditions which are both monochromatic colors, so it's blue and yellow below, then you see there, you should see, in fact, two Brownian bridges. So in his works in the 80s and 90s, though, they were speaking about their surface tension, and for very large Q, deriving that their surface tension for this case, for the conditions blue versus yellow, is twice bigger than for the conditions blue versus free. And then so then one expects that there in fact will be two Brownian bridges, so there will be Brownian watermelon. Okay, so now I just state some results. So together with Piet at the Q equals 2, 3, and 4, we get a new proof for the statement that there's a unique Gibbs measure in the Potts model at TC. So this is continuity of the phase transition. And the ideas are quite different from their original proof. So this was originally proven by Hugo Vadas and Vincent using their parapharmonic observable. So what we do instead, and I'll describe it later in the talk, we relate this to another model of height function, the Six-vertex model. And we use there some FKG that we established for a graphical representation that I will also introduce. At the same time, when Q is above 4, we prove convergence of the interface between these phases to a Brownian bridge. So this was what they conjectured before, exactly. If you put above monochromatic, below 3, you have one Brownian bridge. And if you have above, let's say, red and below blue, then you have two Brownian bridges, which will be avoiding each other. So the condition to not intersect. And then, so that means the distance between them, there will be this for the root n. So you have this emergence of their free layer in between of width root n, roughly. So these are their simulations that I showed you before. Below, so left is their conditions monochromatic versus free, and the right is monochromatic one color versus monochromatic the other color. Now I will explain first the second result. So together with my former PhD student Maurice Dober and Sebastian Ott. So to explain it, I will first define their random cluster model, which of course most of you know, and you saw a mini course about it last week. But just very briefly, so random cluster model is defined on Z2. So just for convenience, I turned the Z2 by 45 degrees because it will be better for later bijections. So here, configuration is a subgraph on this of Z2. Let's say you take a finite part of Z2, you take a subgraph, and your distribution is given by the Piet of a number of open edges, so here in blue, times 1 minus Piet of a number of closed edges, so the absent ones, and times q to the number of clusters. So you also count the singletons. So of course, it's well known that there is a connection to the Potts model that if you just assign to every cluster one of the two, then you obtain the Potts model. So since you assign it independently, then the probability that two points have the same spin, the same color, minus 1 over q is exactly probability that these 2 points are connected by these edges. And we would not need too much from the model, but we need duality. So we will look at their dual configuration. So for every closed edge, we look at the one which is turned by 90 degrees, and we call this dual edge. So this is red edges form a dual configuration, and that there's FKG for all q above 1, positive correlation inequality. So now with this, we'll go forward, and I will just I will to explain the proof. I will actually not fully explain the proof, but I will instead explain the ideas of the proofs for t below tc. This was proven originally. So when you have random, let's say Potts model, t below tc, in fact any q you can take. Then the work of Campanino and Velinik in 2008 proved that their I would say that interface between um, different colors, say blue and yellow, will converge to the Brownian bridge. And speaking about their speaking about random cluster model, what happens is the following: that actually you condition. So since they have different colors on the boundary, you condition on two faraway points being connected by their omega star, the dual in the dual configuration, while your while the connection is actually very costly. But you condition on this to happen, and then you say that, well, this configuration satisfies their FKG inequality and exhibits exponential decay, exponential mixing, and hence you have all the ingredients to develop the Orshad-Zanicki theory to say that this interface, so it's very costly and connects two faraway points. So remind you, this is for t below tc, right? So we look at the cluster, which is very unlikely. So it's already very long, but also since it's so expensive to have more connections, actually it will be also very narrow. So then you will have a lot of renewal points, and then so this is these cone points. And now what happens is actually due to the exponential mixing, you can say that these parts are almost independent. So then if you just replace each of these lozenges by just a step of a walk, then you get to random walk, direct random walk, with steps which will be all kind of not so long, of logarithmic length, and almost independent. And so there's a coupling to the independent random walk, which was shown to converge to the Brownian bridge in a very high generality. So this I here cite the work of Kovchegov, but of course one can also go much earlier than that. Works of Liggett, for instance, and so then the question is that when you have several interfaces, then in fact similar approach would apply. The only thing you have to treat this several random walks at the same time, and this was done in the different works. So, for instance, in Bayofeld, Velinik, and Wachtel for interface over a hard wall, and also by Luca, who's in the room for many interfaces. Well, in fact, what happens is somehow if you have several interfaces, let's say two, then if they get, but they condition not to intersect, but if they get very close to each other, then somehow there is almost no space for them to avoid. So then this just gets disfavored, and then you eventually don't have these points where they come so close to each other, and eventually they just they repulse each other. Well, the main problem with this approach to apply for to t equals tc is that in fact the random cluster model layer exhibits two distinct external measures, free and wired. So here before T below TC, there's just one measure, which is wired. And for T above TC, you have two, free and wired, and somehow you cannot hope to have such a strong exponential mixing statement. But somehow, if you see some configurations even far away, you will still know in which state you are, in free or in wired. So then, which means that you actually need a different graphical representation. So now I will show a slide with several models and several connections. Some of them I'll explain later. So first, Potts model, which we discussed before, this one with many colors, which is connected to random cluster model via Edwards-Storkold coupling. Now, later I will explain that random cluster model can be mapped to the Six-vertex model on the right picture, which is their height function on Z2. And in fact, the latter has some edge representation or some sort of decomposition, uh, which is also linked to the Ashkin-Teller model uh, via the edges, this blue and red ones. Sort of, well, at this stage, you can view it somehow, there's some decomposition, meaning that when you're conditioned on some red circuit, everything inside and outside are independent. So sort of the main message is that in this model, in this edge model, in fact, you will have a unique Gibbs measure. So somehow you go from the measure Potts model with Q plus 1 states, then you go to random cluster with 2 states, you pass for the height function, eventually you end up in some other edge model with only one Gibbs measure. So of course, then you pay some price for this. You have this complicated model, in fact, with two edge configurations coupled to each other. So you have to, proving some exponential mixing statements for it is not trivial. But with several works at hand, we could do it. So this is starting from my work with Ron, which was mostly on the Six-vertex model and on infinite volume limits. Then with Aun, Yasin Aoun and Maurice Dober, and which was strengthening statements to exponential mixing, and finally their work of Sebastian Aoun from last year, which was proving a general statement about strong mixing properties. All right, so message is that if you have T below TC, then you can do it straight away for the random cluster model, where also mixing is easier to obtain. And when you're at TC, then you're well, you have to consider different edge representation, and also well, you have to sweat a bit to prove their mixing statements. So now I will explain the coupling between the random cluster and Six-vertex model. This is their seminal Baxter and Wu coupling. So we look at their self-dual point of their random cluster model. So in this case, this weight can be rewritten as root q to the number of loops. So loops are drawn between blue and red edges, as you see on the right picture. So again, left picture is random cluster model, blue is primal, red is dual, and then you draw this loops between primal and dual, and then well, afterwards you can rewrite root q as is e to the I lambda plus e to the minus I lambda. So for this slide, maybe it's best to assume that C is at that Q is at most 4. Like this, root Q is 2 times cosine lambda, and lambda is real. So then you rewrite root Q as e to the I lambda plus e to the minus I lambda. So these are two possible orientations of the loops. So you get this, now you decompose this in different oriented loops. And now each loop you can cut into different arcs. And somehow the point is that then you afterwards merge the two neighboring arcs together at every vertex, and if they're oriented in different kind of in different directions, then the product is 1 e to the I. So each so maybe the key step is that each loop which is oriented clockwise receives weight e to the I lambda, and it has 4 more right turns than left turns. So then each right turn is given is I e to the I lambda over 4, and left turn is e to the minus lambda I lambda over 4. And then whenever you have these arcs going in different directions, then the product is 1. And if they go in the same direction, then the product is e to the I lambda over 2 or to the I minus I lambda over 2. And in fact, for every vertex with two incoming edges horizontally and two outgoing vertically, or vice versa, you'll have exactly both possibilities. So each vertex will have weight, uh, which is written here, just two times cosine of lambda over 2. And this brings us to this model with which is six-vertex model. So for every vertex, you have two incoming and two outgoing edges. So this is the gradient of a height function, because around every vertex, you have no, it's color free. So then this is drawn on this left picture. Just for every two faces, you say that whenever their arrow is drawing up, the face on the right has a higher height, and whenever it's drawn down, well, on the contrary. So that's the connection. Again, this I'm going somewhat quick from this because I assume that Johan also covered this in his mini course. Overall, this connects their two model, so they're random clustered six-vertex model. And now, in fact, one can go one step further and in there add in this coupling also some defect line. So you're putting some defect. So for every edge, which is between these two vertices, U and V, for instance, just draw some defect line. You say that you pay some price if the edge is going up, and some other in the opposite if it's going down, and then then you can rewrite, in fact, the same exact coupling will give you a Fourier transform of the height function. So this was, at least I saw it in the work of Jubida. If there are early references, I'll be happy to see it. Yeah, please let me know. And so then this Fourier transform can be rewritten for a random cluster model for the function of some loops surrounding these two vertices U and V, either just U or just V, with particular, the function is written here is some specific trigonometric polynomial, but I will not get too much into details. The main point is that if you look in this our regime of parameters and you fix some particular value of alpha, and in fact you have a bound that this right-hand side is at least probability that those 2 points are connected. Because if they're connected in the random cluster model, then there's no loops at all. And in this case, you get just value 1. And in other case, you get a value which is non-negative. And since you have this bound of their probability that 2 points connect by this Fourier transform, well, in fact, this one, if the function delocalizes, will converge to 0 because you will average. It's a bit of a story, like you average roots of unity over a circle, and you get 0. So it's not difficult to prove that you'll get 0 whenever you have delocalization, meaning that the variance of the height function diverges. So then it means that if you prove that the height function delocalizes, then you immediately get from this that the random cluster model, the probability that two vertices which are far away connect to each other decays to 0. So there's no infinite cluster. So this is the connection between delocalization and the existence of an infinite cluster. So then in the rest of my talk, I will, well, not at least for the next one to three slides, I will focus on proving delocalization. And this once you prove delocalization, due to these connections, you will also get continuity. And basically, this is I don't hide anything really here. It's a complete argument. I mean, okay, I do hide something. There's in fact, one has to consider this on a torus, and this becomes a bit more messy, but otherwise, it's almost a complete argument. So now I will just say a couple of words about Six-vertex model. So this is their here kind of it was not really defined, but you see it on this bottom picture. So at every vertex you have two incoming and two outgoing edges. So it's four choose two possibilities, six possible local configurations. If you fix then if you fix zero at the left bottom corner, then all the other heights are determined, and there are six possibilities. These two receive weight A if you have the arrows. If you have agreement on their along this diagonal, which going from southwest to northeast is the agreement. In the other disagreement, you have weight A. If the other diagonal agrees and this one disagrees, weight B. If both agree, this we call saddle points, and you have weight C. Probability is proportional to just A to the number of A vertices, B to the number of B vertices, and C to the number of saddles. Simulations are shown here. So here I take A equals B equals 1. And if C is low, then you have this delocalized picture. So here, different heights are shown in different colors. And you have a big cluster of height which is different than what is on the boundary. And if you have C which is large, like 2.4, then actually you have tiny clusters of different heights, besides those which are on the boundary. Okay, maybe I'll just mention the works which are about the Six-vertex model. So this starts with free energy computations, which led to their conjecture of their phase diagram with delocalization for all C, which is below A plus B, but above B minus A and between B minus A and A minus B. So of course, the dimer arc is when C square equals A square plus B squared. And here the GFF convention is known. And additionally, the conversion is proven also when you have their interaction between dimers. So it's some kind of in some neighborhood of this line. Then localization was proven in this whole triangle, and delocalization was proven originally in the uniform case, and then extended to first by marching to a part of this pink line, and then by Hugo, Alex, and Jon and Mendes to the whole purple line. So this is A equals B, and C between 1 and 2. And moreover, a very strong result, which was also discussed last week in their mini course, is rotation variance. So in this turquoise part of the diagram, rotation variance was proven. And soon this will be used to get their GFF convergence, which is we're all looking forward to. Let me also briefly mention that in the other parts of the diagram, so their results by using representation theory, which rather speaks about the behavior next to the boundary. So this I will not really discuss in this talk, but I just want to mention that there are many connections. So basically, what will prove the Piet is a new proof of this delocalization, which specifically also extends the delocalization to their A different from B. But the main thing is that it's somewhat different in flavor from before, which hopefully can be also useful in further investigations of this model. And so this is on the diagram, the green part, and we get new proof of the log delocalization, logarithmic bound, that indeed the variance at the origin grows as logarithm only when in the symmetric case when A equals B. So the other case actually remains open, A different from B. So their main ideas are soft tools soft probabilistic tools, which are planar duality, positive correlation inequalities, and this height function decomposition, this graphical representation, which I mentioned earlier, and I will describe it very soon. And the connections, so since we don't use paraharmonic observable, in fact, this proof extends to the model which is not known to be integrable, which are Lipschitz functions on their triangle edges, which I will also describe later on. And continuity of this also gives a new proof of the continuity of the phase transition in random cluster and POTS models, which I mentioned earlier. So what remains open somewhat, so one is maybe shamefully open is this logarithmic bound on correlation on their delocalization for A different from B. So it's known that on this pink line you do have logarithmic variance, like you should in something which should converge to the GFF. But out of this line we don't know this. And of course it is very natural question to extend this rotation variance proof from there from this region which is in blue here to the whole triangle. And there's a problem because actually it uses random cluster model, which is not possible to do outside of this part. And then, yeah, so hopefully maybe some of these tools which are described in this talk can be useful or not for this kind of problems. Now a short argument of how to prove delocalization for uniform, first in the uniform case, and afterwards I explain how to extend this to a non-uniform case. So we imagine that we put boundary conditions which are one, and we assume localization. So assume that when we let the box go to infinity, the limit actually exists. And for now, we assume ergodicity. In fact, this is non-trivial statement, which I will comment on later on, but so far we just assume it. To get this height function HF1 measure under one boundary conditions. Now we'll look only at even heights, but we'll look at them in the triangular connectivity. This is this red heights at triangular connectivity. So their non-coexistence theorem due to Zhang and Sheffield, well, allows to derive the following, that if you look at the heights which are below 0 or above 2, they cannot percolate. Why is that? Well, because you have FKG for the heights, then so it's ergodic measure. So then either both percolate by symmetry or none. But if they both percolate, then they have two infinite clusters in their model and its complement, and that is ruled out by the non-coexistence. So none of them percolates. But if none percolates, you can also it means that this infinite cluster of at least two is blocked by circuits of at most 0 at every infinite. Well, there must be infinitely many circuits of this height at most 0. And in fact, you can apply the same approach to their height function under 0 conditions, and you get infinitely many circuits of height at least 1. And moreover, you can couple these two measures just by shift 1, such that in such a way that these circuits actually almost coincide. I mean, they just shift by the other by 1. But under these conditions, well, if you look at the red measure, this at most 0, in fact, the best which you can have at this blue point is 1, because next to 0 you can have at most 1. So in fact, the best conditions under this which you get for the red measure is 0, 1. And the worst condition we get for the for the blue measure is actually 0, 1 as well. Because you know that at this blue circuit you have at least 1. So the red one you have at most you have at least 0 afterwards. Which means that you find a circuit in which this blue measure under 0 conditions dominates the measure under 1 conditions. Well, that's a contradiction because of course the conditions 1 are larger. So if you have this domination, in fact, you have equality, and then means that you can also go one step further and say that the measure under 0 and 2 conditions are the same, and this is just a contradiction. Okay. So now going back to so this whole argument actually doesn't really use anywhere the measures uniform, besides one point that their measures are ergodic. So this statement is non-trivial, and it proof relies eventually on absolute value of KG for the heights, and in fact also right and afterwards so for absolute value of KG gives you that under 0 conditions, you get sort of minimal, these are minimal conditions. So then in the limit, you will get their measure which is ergodic, but only for the absolute value. To get from this ergodicity for the whole height function, you also need to prove that the clusters of non-zeros somehow will not really be infinite. And this is again a result of non-coexistence because their zero heights are most preferred. So you cannot have infinite clusters of one if you have infinite clusters of zeros. Okay. So now what to do if you actually have non-uniform measure? So this fact is indeed used is in the proof of this ergodicity. So I will mention it again now. What exactly is so specific? So if you look at any C between 1 and 2, so now you assign this weight to their configuration which has agreement on both diagonals. And all the other ones you assign just weight 1. Now you introduce the following representation. You connect two edges of height 0 by an edge. Automatically, if the other two are different, -1 and 1, and you connect it with some probability if the other two are the same, both ones or both -1s. And you choose a probability exactly to be 1 over C. So if you have this configuration that both agreements zeros and ones, then you take this edge of probability 1 over C independently for different vertices. And why is 1 over C so special? Well, because if you actually have this configuration with an edge and the other two heights are different, -1 and 1, then your weight is 1 and you force this edge. So the overall weight is 1. And if you have this edge in the configuration where the other two heights are the same, 0, 0s and 1s, 1, then in fact this configuration, this local weight is C, and you take this edge of probability 1 over C. So overall, the weight of this local configuration is 1 again. So in fact, if you have this edge, 0, 0 edge, then in fact you don't care if the other two heights agree or not. This allows you to sort of to disconnect to remove dependency between these odd heights. So in fact, in particular, if you have a circuit of these red edges, it will be domain Markov. So you just know that on the circuit you have zeros, and otherwise you don't know anything else about the measure. That will be your boundary conditions. That's where somehow this allows you eventually to reduce the case of non-uniform measure to the uniform one, just considering these zero edges instead of considering zero heights. So these edges you see in the right picture, some of them are forced, like between 1 and -1, and some other ones are not forced. Like in this corner on the right bottom or top corner, you have 0, 0, 1, 1. Here you just toss a coin, maybe you take this edge, maybe you don't take this edge. And to eventually use non-coexistence for these edges, we have to have FKG, which we proved with Piet, that indeed these edges are FKG. In fact, you also, which I want, so far I hid a bit under the carpet. Eventually, you have to also to prove this non-percolation. You want to have this intuitively correct statement that if you have zero conditions, somehow you prefer zero edges versus something else, and which eventually relies on their statement that afterwards you consider also these edges for other even heights, and actually you also have to define the edges on the odd heights, which will also decouple interior and exterior. So eventually what will happen is that in the interval between 1 and 2, you have you have some sort of superduality statement that whenever you sample there, so at every vertex you have either blue or red edge, and in fact maybe both. So in particular, the dual configuration to these red edges will be included into the blue one. So then when you want to prove that you don't have no percolation in a dual configuration, it's enough to, so maybe very briefly, the proof is the following, that so you want to prove ergodicity. So you sample your under zero boundary conditions. So the only thing which can break it is if you have infinite cluster of these non-red edges. They're dominated by the blue ones. And the blue ones, in fact, have also small distribution on the red ones because conditions favor favor the red. They're the best for the red. That's kind of the whole argument. And so if you have the dual infinite cluster in red, you have also a primal one, and this is the problem with non-coexistence theorem. So, and in fact, exactly the same argument extends to the Lipschitz functions. So here we look at triangle edges, and distribution is given to by look at triangle edges or faces of the hexagonal edges, and between two neighbors, difference is at 0 or 1 or minus 1. Like on this picture, we draw these level lines. Probability for configuration is given by some c, well, the same as before, times to the power of number of neighbors which have the same height, divided by 2. So divide by 2 is just to have the same parameters as in the previous slides. Well, what is known about this model is that what we proved in several works is that if you have this C, which is above 3 minus epsilon, then you have localization. So again, the C kind of favors the flat points, flat edges. So if you have large C, you have flat function. If you have small c, you have rough function. Between 1 and 2, we prove that there is delocalization. And so far, we don't know what happens between this 2 and 3 minus epsilon. One expected it localizes, but we don't know this. And also the question of Lipschitz functions on Z2 is completely open. So what we discussed before is this height function of graph homomorphism on Z2 and Lipschitz functions on triangle lattice. But if you put Lipschitz on Z2, you don't know. And the proof extends in a rather direct way. So now look at now you rewrite this probability of a configuration via triangles. So far you count number of edges where you have the same height. In fact, there is some combinatorial property that it's just enough to look at their triangles, which have all the same height. And meaning, but then you just have twice less of them. It's because of the bipartite property that the hexagon is bipartite, and you have twice less these triangles than these edges. And then once you have this picture, it looks exactly like in Six-vertex model, and you do exactly the same thing, but on triangles. So you're like modulo the one important phenomena that you're now for this triangle, let's say you accept not height 0, but heights 0 or 1. That's your, if you have height 0 or 1, but not all the same, you automatically put the red point. If you have different heights, you automatically don't put the red point. And if you have all zeros or all ones, then you put this red point of probability 1 over C. Again, meaning that if you have red point, you have weight 1 independently of the heights which are around it. That's its decoupling property. So again, so here on this picture you have this have the red vertices drawn. So I drew them also on at other heights because eventually it can be useful. But you can also look at those which are at 0 heights or between 0 and 1. So some of them are forced, like between 0 and 1s are forced, and some of them are not forced, like at the 0 heights. By the way, this is also, so this idea to look at the 0, 1 heights is also is mentioned central in the work of Alex Carrillo from 2023. Somehow here I give an interpretation of our proof, which is using the 0, 1 heights. Originally, our proof was written for a bit different objects, but it's just easier to treat it in this way. And so the point is, if you're again this 0, 1 vertices, so these red vertices, they again FKG like before, the circuits of the Markov like before, and again like before, we can prove that they're limit on these conditions. Now, if before you had 0 conditions, now you have the 0, 1 conditions. So on the boundary, you hide the 0 or 1 given by these vertices. Is ergodic. You use non-coexistence theorem to say that there's the heights below 0, above 1 don't percolate simultaneously. By symmetry, under these conditions, either both percolate or non-percolate. So both cannot percolate, so none percolates, and eventually meets the amphetamine level lines and delocalization. Just to be clear, sorry, when do I have to stop?
305, 310, sometime between there would be great.
Uh,
310.
so
Yeah, about 10
yes,
minutes.
I'm a different time zone. Sorry. So how
Sorry,
many
sorry,
minutes
sorry.
do you
So,
have?
sorry. About 10 minutes.
3 minutes. Sorry. Yes. Okay. Very good. I will not. Yeah, I will not need this time, I think. Um, so now maybe remaining part is that, well, what happens actually? So here the FKG is used in a crucial way because we uh, well, specifically to prove this ergodicity, to prove that, well, we have some minimal maximal conditions on the boundary, we let them to infinity. That's the standard way to go. But also it's used afterwards in a proof in this non-coexistence result, because this, of course, is false if you don't have FKG. But now imagine for a second we don't have FKG. So now the first part I cannot really recover. I have to assume that you have some ergodic measure in the limit. But the second part I will somehow manage to correct. So now what we look at is the following object. So we look at any ergodic infinite volume measure, and we forget about heights. Now we don't have heights. We have only level lines. So since for every level line you have two possibilities, either it's oriented clockwise or counterclockwise, depending on the heights being bigger inside or outside. So your probability of a configuration on these level lines will be given by 2 to the number of loops times the C. Well, before what we had is this 2 to C to the number of triangles where all heights agree, which means where no level line passes, which is C to the number of vacant vertices, and specifically this type, right? This bipartite graph, vertices can be of this type or on the reverse. We look at only at those which correspond to the upward oriented triangles. That's your measure. And you take any ergodic infinite volume measure and for this finite volume distribution. So the point is that the key to proving delocalization was to prove that the circuits it's enough to construct the circuits of red vertices, because you know what, they decouple interior from exterior. So if you have infinitely many of them, eventually you will have a delocalization, because every each of them you can flip the height inside compared to outside. But to prove that the circuits of red vertices exist, it's enough to prove that the other ones do not percolate. Then by duality, you have the statement. Now you look at the gray vertices, which are shown here, and in fact, so then you can interpret this representation from before. So if you hear we specified some values of the heights, and this sometimes force some red vertices like between 0 and 1. You have to put this red vertex in between 1 and 2. You cannot put it. In fact, somehow, if you now forget about orientation for loops, this will mean that for every loop you toss a coin, whether you color it red or whether you color it gray. So in fact, what you have is for these gray vertices, you have a percolation on loops and vertices, which are vacant. So in loops, you have percolation probability 1/2. Probability 1/2 is oriented one direction, and you take this in gray, and probability 1/2 you don't take it, it's red. Like on this picture, this is a red loop then, and inside is a gray, and the side has two red loops. And for vacant vertices, you take probability, which is before it was 1 over c, right? We took this probability 1 over c, so it's gray of probability c minus 1 over c. And since c is between 1 and 2, actually this is at most 1/2. And so um, now I will well, somehow so what you have to do, you have to study this percolation on some more general graph on the slopes and vertices. And this brings me to my work with Harel, sorry for misspelling his name. It should be H.A. Harel and Zalesko from last year. In fact, if you take any planar graph and P, which is most 1/2, and you do Bernoulli type percolation on this graph, then you have either infinitely many or non-infinite clusters. And then if you're, so here with the percolation loops and on these vertices, one can easily draw a planar graph on them. And then one can also rule out infinitely many infinite clusters just by amenability, since you measure ergodic, so it's shift invariant, you use Burton-King argument. And then it will imply that, so infinity is excluded, then there's no infinite clusters. So then, in fact, we prove what we wanted, that indeed there will be infinitely many red circuits, and hence in the height function it will be delocalization, but also this extends to their loop one model, which proving that there belong loops in some part of the diagram. I don't have the time to define this model, and I don't think it's really so important for this talk, but somehow the point is that you can replace some part of this tools of FKG by this general planar graph statement, which is also linked to the conjecture of Benjamin Schramm from 96. So the summary, so what happened in this, to discuss in this talk, that the height functions linked to many different models, including Potts model. There was different height functions like Lipschitz functions or graphomorphisms, or also linked to Ashkin-Teller model. And the point is we can treat dependency via graphical representations. This is the idea from Edward-Sokol coupling. Somehow, if you sample an edge, you just decouple some part of your configuration. And in fact, one can avoid use. Yes, sorry. Yes, so to the point was this was on the last on the previous slide, that we can avoid part of the use of FKG inequality by considering percolation on general planar graphs. Somehow, so often one needs the symmetries of a lattice to use ergodicity, and we do right, but somehow for intermediate step we don't have to assume anything. So how that's the point, and this is very can be very helpful. Hopefully, also for other models, if there are any ideas how to use this, I'll be very happy. I'll be very happy to hear. So then, what remains open? So for this question of convergence of the interface for Q above 4, in fact, we proved this for two different cases, which is under free wired and wired wide conditions. But overall, the question of the even definition of the surface tension remains open. We didn't define it. We just went to the other model, brought mixing to this edges of their Ashkin-Teller model, then used it as unique measure for unique measure, and then brought back the statement of convergence. But then defining surface tension will allow to really treat more general boundary conditions. Again, Lipschitz function on Z2 remains open. Interplay of this graphical representation that I discussed in this talk with Young-Baxter is completely unclear. So far, it seems to be not working well together. Young-Baxter works well with both models random class and Six-vertex, but these edges seem to these edges of their height function decomposition just do not couple well, unfortunately. And of course, there's it's tempting to go beyond C above A and B. What about this white region? Is there some other representation with other edges or other vertices which will tell more about the model? And I'll stop here.
Okay, so let's thank Sasha. Any questions?
Thanks a lot for the nice talk. So what's next?
Right. No, what's next is I think it is worth if we're talking about Six-vertex model, I think this log delocalization statement that proving logarithmic bound on the variance it should be feasible one way or the other, as was discussed at some point. And yeah, otherwise, I'm very curious to see if this one can apply these edges to somehow uh, to derive more precise statements about the six-vertex model, because somehow so far random cluster model seems to be more useful to get this statement, to get this. But for some statements already, we managed to go in the reverse direction, right? So we managed to go from Ashkentela to Potts model. So I wonder if this can be done also in this instance of, for instance, this region which is green but not not turquoise and not pink or anything. So maybe one can extend these regimes of behavior.
Thank you.
I also have a question. Hey, do you believe that the result that you proved with Moritz and Seb, you can use it to tell something about a Fourier transform of the six vertex, but in the localized phase, like the I don't know, like the asymptotic of sort of 2-point functions of the six vertex in the localized phase.
Right, thanks. So I think if I just go back to this Baxter, yeah, BKW coupling, so what will happen if you have C, which is here above 2, which means Q will be above 4, and in fact, everywhere you should remove I. So that's the statement. And then you don't have Fourier transform, you rather have the Lammers transform, but you do have a coupling. The statement still holds, there's no problem. I think that's not an issue. But yeah, that's correct. I don't know. Yeah, I don't know if one can get anything more from this. So here, yeah. So it depends on the question, right? So if you talk about the question like correlation of two edges, I don't think this will tell it.
Maybe, for instance, it allows you I mean, on the random cluster model side, it allows you to get a very precise asymptotic on a sort of ratio of two partition functions. And maybe it's very vague, but maybe I was expecting that you could import something of this result on the side of the six vertex with the coupling that is given with BKW.
Yeah,
It's very vague.
I think regarding precise results, somehow beta ansatz brings it as precise as possible for the six-vertex model, and then you can bring it back to your random cluster. In fact, this was it was done, right? So the work of Hugo, Maxime, Johan, Vincent. So they proved that Matan, the correlation link was computed, for instance. So they're more or less using this similar equations. So in fact, it was going actually from a six-vertex to random cluster because of beta ansatz. And I think that's as much as you can get probably.
I have a very quick naive question. So what's the defect line there? I don't understand what you call defect line.
So right, so yes, sorry, I was not very precise about this. So which means that you take two vertices and you say that for so for every so you draw this imagine you're on the same these two faces and it's separated by this line of edges of vertical edges, for instance, and then for every edge which is oriented upwards, you will get e to the I alpha, and downwards e to the minus I alpha. So then so then in your height function, so in the left you get this potential. So you get this function. So for the difference between the heights, you will get this weighted e to the I mean the Fourier transform. And on the right, so for every now you can see it for every loop which goes around only u in the direction which is positive, you will get contribution which is exactly one edge in between in this alpha defect line. In the wrong direction, it will be minus alpha, and the which goes around v, it will be the opposite. So in fact, you will that's if you go for this in this coupling, then the loop which goes around only u will receive the weight instead of receiving the weight 2 times cosine of lambda, it will receive the weight 2 times cosine of lambda plus alpha, and about around uv to be lambda minus alpha. That's and then you just so that's the connection. So the defect line specifically just means that you take a bunch of arrows and you say that whenever somehow whenever the loop crosses so each edge going upwards receives the additional weight into the alpha and down into the minus alpha. That's the point. Okay.
Okay, thanks. So let's thanks Sasha again.
Thanks.